Thank you very much for the introduction. And most of all, thanks the organizers for inviting me to this conference and for organizing such a great meeting. It is indeed a pleasure to be here. So my name is Tomasz Smolenski. I'm currently a postdoctoral researcher at Attached Mamoglu Group at ETH, but I will soon establish my own group at the University of Basel. And today I would like to talk about magnetism of electrons in the moiré lattice, but in contrast to the previous two talks, I will actually use optics to probe this magnetism. And it will be actually quite unconventional type of magnetism. So, after all of these great talks during this week, I hope that I do not need to convince you that two-dimensional materials provide a unique platform for uncovering like new kinds of many-body interactions. So basically, we have all of these, two-D materials. We can exfoliate them, stack them together, form any conceivable order, stacking order, and this gives rise to basically devices with new functionalities. So particularly interesting from the perspective of my talk and my research is basically that you can twist or introduce a moiré superlattice by taking two monolayers and twisting them with respect to each other. And these basically folds your conduction band or valence band and gives rise to these flat mini-bands, which basically quench the kinetic energy of your electrons. And if you quench the kinetic energy, the interaction effects start to play a more important role, and it gives rise to formation of these, strongly correlated electronic phases that since 6 years have been discovered in many different systems, starting from graphene through then TMD bilayers. So, now the efforts, of course, were both on electronic correlations and on collective magnetism. So my talk will be actually focused on the spin physics of these electrons that are injected into moiré lattice, and their spins are interacting, so it can give rise to emergence of some non-trivial collective magnetism. And when you think about, just in general, what kind of correlated magnetic phases you may expect in this system, there are many, but you can think about two limiting cases. So the first case is the one that was actually discussed in the previous talk, which is when you have two layers which basically have degenerate conduction bands, and the electrons can tunnel between them, then these bands hybridize, right? And this can give rise to these topological flat bands, which have non-zero Chern number, and then it can host these, fractional or integer chain insulators that are ferromagnetic. So on the opposite end are is kind of a situation where your bands are split, and there is actually no tunneling between the layers. And in this case, in the lowest energy, you can think of having just a single flat miniband, which essentially realizes a Fermi-Hubbard model, if you can think of it like this, where you can, fill the different moiré sites with just electrons that can have a spin up and spin down. And this is exactly the case on which I will be focusing on. And, if you think about, the interactions between spins of electrons in such a case, you usually would think about exchanging energy, right? So basically, the electrons would basically try to minimize their Coulomb repulsion by aligning their spins in a particular way. So this is like how typically magnetism emerges in materials. And what I am going to talk about is a very different kind of magnetism, which is driven not by exchange, but by kinetic energy. So basically, the electrons arrange their spins in order to minimize the kinetic energy, which is quite unusual. So before I show you the experimental data, let me first thank my collaborators, so particularly the group of Attached Mamoglu, including Livio, so our former PhD student with whom I carried out these experiments. We also got the theoretical support from Eugene and Yang Zhang, and we get our HBN crystals, of course, from Kenji and Takeshi from Japan. So now, when it comes to the experiments, the system that we are studying is a bilayer of tungsten sulfide and molybdenum diselenide. This is angle aligned, so it has zero twist angle. And due to lattice mismatch, there is a moiré superlattice with roughly 8 nanometer of a lattice constant. And this system has few advantages. So first is type 1, so both the conduction and valence band minima are in molybdenum diselenide, so it is very nice optical properties. The exciton transition is very narrow because there are no non-radiative channels, and we are indeed dealing with a lowest energy flat band located in molybdenum diselenide, and we can fill it with electrons using our gate electrodes that we can apply voltage to and controllably inject the electrons to the system. Now we probe their magnetic properties optically, as I said. So we load this device into a dilution refrigerator that allows us to cool it down to roughly 100 millikelvin, and then we have, our positioners that allow us to basically select a spot on a sample and to focus our light on this spot to a submicron size spot. And what we probe is that we probe the white light reflection of such a device, and here you can see how such a white light reflection evolves when we fill our flat band with electrons. So you can see there are a few transitions. You've heard about their origin yesterday during the talk by Alex Hügele, so I will not go into the details. What I'm going to focus on in this is this lowest energy transition here, that basically emerges in the spectrum exactly at the onset of filling the band with electrons. And this transition, you can think of it, we call it attractive polaron, but you can think of it essentially as a collective excitation of tryons at each moiré site. So what is a tryon? Basically, tryon is a free Baget object. It consists of an exciton that we excite optically and the resident electron. So now, if you want to excite a tryon at the given moiré site, there has to be an electron at this site in the first place in order for this to be possible, right? So basically, this already tells you that the intensity of this transition should be proportional to the number of singly occupied sites. And this is indeed what we observe. So if you plot this intensity as a function of filling factor of our moiré lattice, this intensity initially increases as we, keep filling the sites with electrons. Then it basically becomes maximum when at the unity filling, so where we have exactly one electron at each moiré lattice site, and then from this point on, the electrons that you add need to form doublons at already occupied sites, and these doublons cannot then contribute to the tryon formation because this site is then blocked, so then the intensity of our transition goes down. Okay, so this is one thing, but from the perspective of what I'm going to talk about, the most important fact is that in order to form the tryon, the spin of the electron at your moiré lattice site need to be anti-parallel to the spin of the exciton that you create optically. And this spin of exciton you control with the polarization of light that you send into your cryostat. So basically, what does it mean? Well, it means that the intensity of our transition in a given circular polarization is proportional to the number of electrons with a given spin orientation. So up for sigma plus and down for sigma minus. And you can, check it out very easily. If you measure your polarization resolved reflection of this transition at zero field, where electron spins are random, you get the same response in both circular polarizations. Whereas if you do it at non-zero field, one transition is clearly stronger than in the other. And I know by measuring the polarization degree of this transition, you can directly determine the spin polarization degree of your electron system. So it is a pretty convenient way to basically access the polarization properties of your electrons. Now, how we implement it in practice is that we measure this polarization degree as a function of magnetic field. Here you can see an example of such a curve. It initially increases around the zero field, and then it saturates when we fully orient the spins by magnetic field. And now, important quantity is this, susceptibility. So this is this slope of increase of our polarization degree at zero magnetic field, because this magnetic susceptibility of the system basically carries the information whether or not the spins of your electrons are correlated with each other. And how can we access it? Well, if the spins are completely uncorrelated, then if you increase the temperature, this susceptibility will decrease with temperature inversely proportional to the temperature, as it is the case of a paramagnet. Whereas if the spins are correlated, you expect usually a more complex behavior with some Curie-Weiss law, this theta here, that this Curie-Weiss temperature being positive if the interactions between spins are ferromagnetic, or negative if they are antiferromagnetic. So now let's check it out. So in order to do it, we basically measure the inverse susceptibility as a function of temperature. We then fit it with linear line, and the point where this line intersects with the horizontal axis is basically this Curie-Weiss temperature. So you can see that depending on the filling factor, these temperatures can be very different. Above the unity filling, this temperature is close to 0. Here it's highly negative. And this trend is actually reproduced if you measure it as a function of filling factor. Indeed, the moment you go below unity, this temperature sharply drops, and it goes actually to minus few Kelvin. So this would by itself suggest that actually we are dealing with strong antiferromagnetic correlations below unity filling factor. And this result by itself wouldn't be actually very novel. So this has been observed in many different systems by other groups. But I want to point out that with this interpretation, one has to be really careful, because in our system, this is actually not reflecting any magnetism in the ground state at all. And how do we know this? Well, we changed the excitation power. So as a matter of fact, our experiments are carried out at relatively low power of roughly 100 nanowatt, at which the density of our excitons is many orders of magnitude lower than the density of electrons. Still, if we carry out the same experiments at lower power by a factor of 4, you see that the data actually still nicely follow the Curie-Weiss fit, but the extracted Curie-Weiss temperature is sizably lower. And you can keep doing this. You can, reduce the power even further, and this Curie-Weiss temperature actually approaches 0, independently of the filling factor. So what does it tell you? Well, it tells you that this apparent decrease of Curie-Weiss temperature that we observed is actually not a property of the ground state of the electronic system, it's just the spin heating. So what we are actually doing is that by injecting excitons to the system, these excitons have a finite chance of depolarizing the electron spin, and this way they are affecting the magnetic state that we are actually trying to measure. And this is also existing in a monolayer system. We observed it 2 years ago also for the simple TMD monolayer system. So this is quite universal, at least when it comes to molybdenum diselenide. So now, in order to avoid it, we are basically decreasing the power, and it turns out that we have to do it pretty substantially. So we go to unprecedented powers of picowatts, and then actually the temperature, the Curie-Weiss temperature, is very close to 0. So we have to use the Diel-Fritsch to study it. Then it also doesn't depend anymore on the excitation power. So we are sure that at these conditions, the excitons really constitute a non-destructive probe of the electron spin system. So now if you zoom in, you can still do it. You observe the truly magnetic properties of the true ground state. And you can see this is very different as compared to what we would incorrectly infer from high-power experiments. So nothing is actually happening below unity filling. There, the Curie-Weiss temperature is almost 0. Whereas when you go to above unity filling, you actually start to see this striking increase of the Curie-Weiss temperature that reaches roughly 100 millikelvin. So it is just slightly below the temperature that we can actually reach in our system in order to observe the phase transition point, so to study the hysteresis. So we cannot do it, but we do observe this clear signature of existence of ferromagnetic correlations in our system. So now, how we can explain this magnetic response? So to do it, actually, we can first start with just analyzing what happens at the unity filling. So in this case, we have just one electron per moiré, like a lattice site, so it's very simple. These electrons are actually trapped there. They form a Mott-insulating state. And, in this case, their magnetism has to be determined by exchange interactions. Usually, in this case, we think about the super exchange, which originate from virtual hopping of electrons between lattice sites. But independently of the details of what this exchange interaction really is, what our experiments are telling us is that this exchange is weak because the Curie-Weiss temperature is essentially 0. So why this exchange is weak? Well, it is a consequence of the fact that moiré potential is very deep, so your electrons are actually very tightly localized at the potential minima. And now you can think of it in terms of a Fermi-Hubbard model, so you can, think about these two parameters, so like an on-site Coulomb repulsion and the hopping term between the two lattice sites. And, DFT calculations tell you that this U is 2 orders of magnitude larger than this T. So now this super exchange is really small because its scale is like T squared over U. So it's very small. Now, what happens when we add extra electrons on top of this Mott insulating state? And this is actually very interesting because if you think about this additional electron, it has to form a doublet at the site that is already occupied. So now, even though these Mott electrons cannot move, this doublet can actually move, right? It can form here, here, wherever. It can form at any lattice site. So by doing this, by moving around the lattice, this doublon can minimize its kinetic energy. But in order for this kind of redistribution of a doublon to be possible, the spins of all Mott electrons need to be aligned in the same direction. Only then the doublon can really hop around and lower its kinetic energy. And this mechanism tells you that this will actually lead to ferromagnetism with the energy that is proportional to the hopping term and the number of doublons in the system. And this is actually what our theoretical simulations also predict, so that this gives rise to a magnetism that is proportional to this hopping term. So it is much larger than the super exchange. And to the number of doublons, so to the filling factor -1. And you can see that there is a quite nice agreement between this data and this theory, which then really confirms that what we observe here is this kind of unusual type of magnetism that arises from minimization of kinetic energy in the system. And it was predicted actually almost 50 years ago by Nagaoka, but this most likely constitutes a first experimental demonstration of this mechanism when it comes to, like an extended two-dimensional system. And one additional confirmation that this is indeed the case is that if you have a sharp eye, you may already observe that we have a substantial drop here, which actually turns out to occur exactly at the filling factor of 4/3. And this particular filling, these doublons, they form a generalized Wigner crystal. So independently of what it really is, in this case, the mobility of these doublons is suppressed. They cannot move. So this gives rise to the suppression of the kinetic magnetism, and this suppression should have been full, but due to the small disorder of moiré lattice, it only reaches like 50%. So with this, I would like to conclude my talk. So I hope that I was able to convince you that this, even non-topological moiré structures that are based on 2 bilayers in which the bands really do not hybridize, they can still allow you to study, quite unusual magnetic interactions. And I really believe that this is maybe this observation of this kinetic magnetism is really a small fraction of what can be studied in the system with many, many states, magnetic states that are still to be explored. And just final announcement is that if you are interested in this research, I'm going to establish a new research group at the University of Basel starting February next year. And if you are interested in joining as a PhD or postdoc and do optical spectroscopy of correlated magnetism, please just drop me an email. So thank you for your attention.
Thank you for the wonderful talk. Time for questions.
Tomasz, very nice work. So do you know the hopping term for the secondary electron that you load into the lattice?
So secondary meaning?
So forming this doublon.
Like a second nearest neighbor? Yeah. Or
no. So I guess there is on-site kind of Coulomb repulsion, so you have to pay the price for loading an electron onto the moiré lattice.
So like a V-term.
Exactly.
Yeah.
And what would be the tunneling or hopping for this second electron?
So if you want to, so if I correctly understand, this is like the Coulomb repulsion between electrons at neighboring sites. This is actually, between U and T, and then this is what you're asking for, or?
So once you load the second electron, right, it will see probably a renormalized moiré potential.
Aha, yeah,
so
okay.
is the hopping of that guy no?
So actually your question refers to a very important point as to, you know, why the hopping on the, like, above unity is different than the hopping below unity. Because, you know, like, you know, if you think about like a very simple model, then you should actually, wait a second, I should have this slide somewhere here. No, I don't have it, sorry. So basically, right. So this is exactly the answer to your questions. So indeed, the depth of the moiré potential in this case is highly dependent on whether or not you have electrons in your system. So the electron that, if you think about the tunneling below the unity filling, so like the tunneling essentially of a hole in your Mott state, then the tunneling is much more difficult because the potential is essentially more deeper. And our calculations show us that the difference is substantial. So it's an order of magnitude more difficult for the hole to tunnel as compared to the doublon to tunnel, right? Because the doublon is tunneling between moiré sites that are occupied by electrons. So then this doublon is experiencing a shallower moiré potential. And the difference is, as I said, very substantial. And this is also the reason why we observe kinetic magnetism only on this site, whereas here below unity, it should theoretically also be there, but due to this difference in tunneling at the two different sites, we do not see it, right?
Any other questions? Can I also ask you a question? Can I understand it to the similar kind of mechanism as the ferromagnetism in manganite?
In
mangan oxide.
Which is?
So there are like lots of like ferromagnetic mangan oxide, right? Like manganese perovskite type of manganese oxide.
But what is the mechanism of magnetism?
Oh, the itinerant, you know, kinetic kind of magnetism, ferromagnetism.
But you mean like a stoner type, or you know?
This hopping of electron aligns the localized electrons.
Yeah, so this is a bit different, right? Because if you think about, so you can say, well, how this is different, this kinetic magnetism, from super exchange interaction? Because in the end, super exchange is also like a virtual hopping, right? You have like electron here, and then, you know, you just think of, okay, so the electron can virtually hop between these two sites, so they would like to arrange their spins antiferromagnetically. So this also, of course, involves hopping, so it's somehow kinetic. But the difference is that this hopping is completely virtual, nothing really hops, whereas in this case, this doublon really delocalizes itself. So it kind of really hops in order to make sure that the magnetic energy goes down. So I would say this is a qualitatively different mechanism.
Okay, thanks.
Thank you.